Okay, well, welcome back, everybody. And we're going to walk through a little bit of the period of a pendulum. On slide number 10 is where we're going to start. So make sure you have the slides open, and we're taking notes with that. Once again, slide number 10. I'm just going to kind of present from there. Okay, so what affects the period of the pendulum in simple harmonic motion? So we did some testing, and we came up with a hypothesis on the fact that maybe mass might have an impact, maybe the displacement or the angle, as well as we also said the length of the string and possibly gravity. So after we did some calculations, we should have seen some of that, and I'm going to talk about that in a little bit. So the lab printout here is kind of what I walked you through already with that thought process of testing each individually, collecting some data, and just kind of sensing a trend as to what that data is going to do for the period of the pendulum. Is it going to increase it? Is it going to decrease it? How will it change it? How will it have effect on it? So we're looking at a pendulum. We like to think of it as transferring from these locations. And really, this is going to kind of front load some information for you we're going to use later down the road. But, we talked about period of a pendulum when we were talking about the graphs as far as later down the road. When we talked about period of pendulum, it is an example of simple harmonic motion. The bob will go from the middle, replace, go out, and back and forth repetitively, hence why it's simple harmonic. There's a change of position, aka this A, B, C, D, E, F, and G, over a period of time, and this allows us to act like a wave, which therefore waves have things like periods, frequencies, amplitudes, and much more. So we can actually see that this is happening here. A, it's at its farthest position away from the middle, hence here. B, C, D is the middle of this wave, and then now back to G. G is going to flow back to A. So when we look at one whole period on a graph, it's from one location all the way through back to that next location. So from the B back down up through that next B again. Not this B, but the next B. Okay? C, same thing. And so on and so forth with all these points. That would be periods. That's what period looks like on a wave. We'll cover that again later on. Always good to talk about now, though. But you will see that A is actually my lowest velocity. Well, it's not moving. It's all potential. We'll talk about potential kinetic energy again moving forward. But A is all zero velocity here. D is its greatest velocity. It's actually moving fastest in the middle spot. That makes sense. From potential to kinetic, back to potential to kinetic, moving forward again. So just a couple ideas of pendulum and what it might look like on a graph. We'll move forward into graphs and simple harmonic motion later on again. So there's a couple things we can measure with a pendulum. We talked back and forth. So it's a hanging weight on a string that swings back and forth. That's the definition of a pendulum. It has a restoring force that wants to go back to the middle. So when I move it from 0 all the way back out to the outer point, it wants to get restored back to that middle. Restoring force is kind of a key beginning idea. I'd make sure to underline this and then kind of just give this definition of it. A force that wants to go back to the middle. So when I am here away, it wants to go back to the middle. When it goes through that, it wants to go back to the middle. Hence, restoring force is always trying to head it back to that original spot where it would have started from without us adding that energy to it like we did. Okay, so the more we go away from the middle, the more it will want to go back to the middle. So actually, one thing about simple harmonic motion is the farther away it goes, the more force it'll want to go back to the middle. So if we just put it right here, just right there in that little spot, and it head back to the middle, it wouldn't move very much. It would not have a lot of restoring force. It just go E, 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 E. But if we move it back really far, it has more restoring force, and those two things are proportional to each other. So what we should have saw is my angle. As the angle displacement increased, this right here, as that increased, it had no effect on the period at all. None. Okay, because the force was proportional to how far displaced it was. So I received more force farther away, hence why it'll take the same amount of time as it would this lesser time, force is proportional to the period of time. Kind of crazy, but pretty cool, actually. Okay, so the further we go away, the more mass's weight is ready to move in the x direction and less to move up and down. That's just saying we're going to receive more force in that direction, like here in figure 7. We'll get into the data just in a little bit more second here. So period of pendulum. Here is our equation. Oops. Make sure to try to get all the notes in here. So period, again, is how long it takes for an object to go 1 cycle. That's our big letter T here. This is the period. And then L is the length of the pendulum. That's our L up above here. So how we can get the period larger is if we get the multiplication larger. So we should have seen in our data that the length, as we increase the length, it made a longer period. So the longer the string, the longer the period. Now, to what value, we weren't sure, but here's the equation. Square root of L over G, G being gravity, and we probably had some thought process. As gravity increased, our time would go down. Well, look at this. If we divide by a bigger number, so let's say instead of 10, we divide by 100, our T is going to get smaller. You divide by 100, this number gets smaller. You divide by 10, this number is a little bit bigger. So a larger gravity means less time or less period overall. We multiply it by 2 pi after we take the square root of it. Okay, so the longer the string is, the longer time it'll take for it to cycle. So we have a small little base string, it's going beep, 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 beep. We have a really large string, we multiply this, we get a longer period in which it takes for it to go from 1 full rotation. G is the gravity plan of the different Earths. Not surprising, but not super easy to accomplish. One thing to remember over here is frequency is 1 over T, or period is 1 over frequency. They are inverses of each other. So something has a longer frequency, or has more frequency, it has a larger period. If it has a longer period, it's less frequent. Okay, we'll see that on graphs a little bit moving forward. So big takeaway here is the impact of how we change things for the period. Notice there's no mass. Okay, we should have seen that in our data. Nothing in here about the mass impacts the period of the time. Okay, we saw that in our data. Mass should not impact the period of time. You can use a small weight, a large weight. Either way, it's going back and forth in the same period of time. Also, we should have seen that the displacement, look at how far I displace it. Is that in this equation? Absolutely not. It could be a small angle, a large angle, but because it's simple harmonic motion, the distance of the angle doesn't matter. If I pull it a far ways, that means I have a great force. They are proportional. If I pull it a small ways, it means I have a small force. Therefore, the period of the time is the same. So is not dependent on the amplitude of its displacement. Boom, right here. Again, in notes, star it, underline it, put a box around it. Might be the single most important thing I asked for you to know today. That is true. Also, the further the object is displaced, the more restoring force it will have. And therefore, it will go back with more acceleration, thus taking the same period for a given mass. 2 huge stars here. Okay? That's basically what I've been saying to you about for the last 5 minutes. So, first example problem, these 2 big takeaways need to be known. First example problem moving forward. So we have a grandfather clock needs a period of 1 second. What length of the pendulum would be hung to keep that clock in a good time? Alright, so here's what we're going to do. We're going to say my period needs to equal 1 second. Okay, and I also know, well, I know in this problem what planet are we on and what is my G on this planet. My G is 10 meters per a second squared. Ta-da! So, what's our equation? Well, T is equal to 2 pi square root of, I don't know what my L is, but I do know my G is 10. So when I start plugging in, I got 1 is equal to 2 pi. And I have the square root of L over 10. Okay, so I'm going to divide by 2 pi. You need to be careful with plugging in 2 pi and divide by 2 pi. So when I plug it in, make sure you do 2 pi together in quotes, because sometimes your calculator is not going to read that clearly. So I'm going to go ahead and do that. So I pulled it up, 1 divided by, and I'm going to put it in quotes. So 1 divided by 2 times pi. Unquote it, enter. You should get 0.159. So I'm going to write that down here. So I got 0.159. This one. I'll just keep that for now. Is equal to, now we have the square root of L over 10. So now I got to square both sides. So I'm going to square, and 0.159 squared equals 0.025. 0.025. Sorry, it's not easy to write on this way, but at least I'm writing. Okay, 0.025 is equal to L over 10. And I'm dividing by 10 here on this side, so I have to multiply by 10 over here. So I should get an answer of 0.25 meters. Okay, well, so that's how long, supposedly, our little pendulum has to be. So I'm going to go ahead and double check it. So I'm going to retype that into my calculator. Okay, when I double check that in, just to make sure I did all my math right, 0.25 divided by 10 equals 0.0225. Take the square root of that, times 2 times pi, and I get 0.9934, so which is basically 1 second, and I got the right answer. So, interesting enough, on the planet Earth, if you wanted a grandfather clock to take 1 second to move back and forth for a period, you would make it 0.25 meters. And this is the size that really all grandfather clocks should be if you want them to go back and forth for 1 second. Okay, so pretty interesting actually, I think, but I am a loser. Okay, so on to the work that I would like for you to do. First thing is we just did one application problem. I think you can kind of move forward doing a few other ones. So the period of the pendulum in spring I probably handed out to you yesterday. The worksheet looks a little bit like this, and you will see the pendulum problems are right here. Now, if you notice on this, I said A through L. So if I go start at A, all the way through L, they kind of manipulate one part or the other, solving some problems, and then again back to O. And what you should see here is the answer key. Will give you the rounded answer, and I think these answers, they use 9.81 for gravity. You're welcome to use that just to get close to the same number, but with numbers we get with 10 should be really close, so you can at least check your work to see, hey, did I get the right answer or not? Again, we're just manipulating L or M or G. Within that, obviously M's not in there, but within that equation, to solve for T is 2 pi times L over G for the period of the pendulum. And after that, there is an ACT reasoning of the period of the pendulum. that I want you to answer in at